Till now, we have looked at elasticity or how material deform in an elastic manner. We have also found out what is a stress state. We have also figured it out what is a state of strain at a given point. We have seen relation between elastic stress and elastic strain. Now onwards, we will be focusing on plasticity or how material deform in a plastic region or how it behaves in a plastic region. So the first thing which comes to our mind is an yield stress, which determines a transition from an elastic to plastic region. So we have seen this in an uniaxial tensile test when we looked at an engineering stress versus engineering strain curve. So where the first portion is which shows a linear region, and it is where the material behave in an elastic manner. So non-linear region is a region where material demonstrate a shape change or a permanent deformation. And the transition from an elastic to plastic region, we figured it out using an yield stress. So when I deform material above yield stress, it undergoes a permanent shape change. Actually, yield stress is a measure of where the plastic deformation starts. So when we consider any material in an application, we don't want it to undergo any plastic deformation. So we don't want a material to enter into a plastic region. So we should not cross an yield stress of that material. But this yield stress is easy to figure it out when we consider a uniaxial tensile test or when we consider uniaxial compression of material, where the stress rate is only along one particular axis. But in reality or in practice, the state of stress is complex. So to find out when the material will start yielding or shows a plastic deformation becomes difficult. But it is very important to find out this point, even if the state of stress is complex. So it is important how the given stress state will cause yielding, because we don't want material to undergo any shape change during its service. So we need to find out a relation with uniaxial tensile test with yielding which caused by complex state of state. Because in laboratories, we can do easily uniaxial tensile test and find out when material starts yielding. And thus, it is very important to find out a relation where we can say that if I given a state of stress, the material will yield or not. So there are certain criteria which has been set, and those criteria are empirical. That means they are experimentally consistent and follow certain rules. So these criteria determine what is or when the material will start to deform plastically, or rather when material transit from an elastic deformation to a plastic deformation. So there are certain rules for this criteria, and the first rule is the pure hydrostatic stress does not cause any yielding. This we have seen when we have an hydrostatic stress state, it causes only a volume change, not a shape change. So we have seen this. And thus the first rule is the pure hydrostatic stress does not cause yielding. The next rule is the stress deviator causes yielding or a plastic deformation. This also we have seen that the stress deviator leads to a plastic deformation or a shape change, and thus result in a yielding of a material. And the third rule is yielding criteria is independent of coordinate transform. So whatever the yielding criteria which we are taking, irrespective of our coordinate system, it should be able to predict that if a given state stress is applied to a material, whether the material will yield or not, and it should be independent of your coordinate transform. So there are two major yielding criteria that we'll be looking at. Those are von Mises criteria and a Tresca criteria. So von Mises criteria is also called as Huber-Mises-Heinke criteria. There are many other criteria which are used to determine yielding of a material, and those are Drucker, Horsford, quadratic yield criteria. But for our course, we'll be looking at these two criteria. Those are von Mises criteria and Tresca criteria. So let's look at von Mises yielding criteria. So we have given a general state stress, and how I define it as, I define it as with 9 components, which has normal components and shear components. This is a general state. We have seen this, and I convert this stress state into a stress state where I just get a principal stresses. Those are sigma 1, sigma 2, and sigma 3. So I can come to a planes where I just have normal stresses acting. So I just have principal stresses. So I can do that. Now I can convert this stress state into hydrostatic stress state, which I have shown here. So here the diagonal components, which are normal stresses, are equal in magnitude, and a deviatoric stress state. So we have seen this, how to convert given stress state into hydrostatic and a deviatoric stress state. So here I define sigma m here as sigma 1 plus sigma 2 plus sigma 3 upon 3. This is a mean stress which we have defined. So we have an hydrostatic stress state and we have a deviatoric stress state. So the first rule which we have seen, that this hydrostatic stress state will not cause any plastic deformation, and the deviatoric stress state will only result in the plastic deformation. This is what we have seen. Now let's figure it out. What is the second invariant of deviatoric stress tensor? We find the invariant for deviatoric stress tensor, that is second invariant for this stress tensor, and you can find it out J2 it to be sigma 11 into sigma 22 plus sigma 22 into sigma 33 plus sigma 33 into sigma 11 minus sigma 12 square minus sigma 23 square minus sigma 13 square. This is J2. And here the sigma 11 you can write it as sigma 1 minus sigma m. Sigma 22 can be written as sigma 2 minus sigma m. Sigma 33 is equal to sigma 3 minus sigma m, and sigma 12 equal to sigma 23 equal to sigma 13 equal to 0. So we can write these values for this deviatoric stress tensor and can find out this J2, which is nothing but a second invariant of deviatoric stress tensor. And when you do that, you can find it out, this second invariant J2, in terms of principal stresses as 1 upon 6 sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. So this is what you can find it out J2 in terms of principal stresses. So you can do this calculation and see to yourself what is the value of J2. Just note this equation or the value of J2, that is second invariant of deviatoric stress in terms of principal stresses, because we are going to use this in an yielding criteria, or we are seeing that J2 will be used to define when the plastic deformation starts. So let's move ahead. So we have also seen, when we discussed about elasticity, that total strain energy can be given as half sigma ij into epsilon ij. And we have expanded this U naught, which is a total strain energy, to be U naught equal to half into summation of product of normal stress into normal strains plus shear stress into shear stress. This is what we have seen, that U naught, that is a total strain energy. Now when I consider a principal stresses, which I can find it out using a given stress state, and I find it out what is U naught for this stress state, where are only you have principal stresses. So you can write it as U naught is equal to half sigma 11 into epsilon 11 plus sigma 22 into epsilon 22 plus sigma 33 into epsilon 33. Here the shear stresses are 0, so you have contribution from normal stresses and normal strains towards elastic strain energy. Now we can write this epsilon 11 into using sigma 11. So we have seen these relations as epsilon 11 is equal to 1 upon E sigma 11 minus mu into sigma 22 plus sigma 33. So similarly we can write for epsilon 22 and epsilon 33, and we substitute these values here in this relation, and what you get is that u naught, that is a total strain energy in terms of principal stresses, as 1 upon 2e sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu into sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. This is a relation you will get for a total strain energy. Now we have used this stress state, and we got this stress state from a general stress state which has 9 components, and we converted this stress state where you just have principal stresses to a hydrostatic stress tensor and a deviatoric stress tensor. We have seen this in our previous slide. So this u naught, which is related for given stress state, was this. So you have this u naught which comprises of a dilational energy which is due to a hydrostatic stress state and a distortion energy which is related to a deviatoric stress state. So dilational energy, which is coming from material subjected to hydrostatic stress state, while the distortion energy is coming from a deviatoric stress state imposed on a material. So you have u naught contribution from dilational energy and a distortion energy, and I write it as u naught equal to uh plus ud. What we have found out here is a total u naught. Now we have to find out a distortion energy, because this distortion energy will give you an idea when the material starts deforming or when the materials will start plastic deformation. So our aim is to find out ud. Now we have found out what is u naught, we have to find out what is ud. So basically you use the u naught term, and in case of sigma 1 1, sigma 2 2 and sigma 3 3, you put sigma m. So when you do that, uh turns out to be 3 upon 2e 1 minus 2 mu into sigma m square. Now which is a dilational energy, I can find it out in terms of sigma 1, sigma 2 and sigma 3 by putting this value of sigma m over here, that is sigma 1 plus sigma 2 plus sigma 3 upon 3, and you can find out what is a dilatational strain energy. And this dilatational strain energy, you get the final value as minus 2 mu upon 6e sigma 1 square plus sigma 2 square plus sigma 3 square plus 2 mu to sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. As I mentioned you earlier that we have to find out ud. So we know that u naught, and we just have figured it out what is uh, and thus ud can be written as u naught minus uh. That is a distortion energy which we have to find out, which we can find it out from a total strain energy which we have got and a dilatational strain energy. And when we do that, you just have to subtract these two terms and you get a value of ud. And you get a value of ud as 1 plus mu upon 6e sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. This is the value of ud, that is a distortion energy you get. Now I write it, this distortion energy in terms of J2, which is nothing but a second invariant of our deviatoric stress tensor. So we have figured it out what is J2. So this term I can write it as 6J2. You just go back and refer our previous slides and you can find it out that this term you can write in terms of a second invariant of deviatoric stress tensor. And the ud I can write it as 1 plus mu upon E into J2. and this term I can replace it with a shear modulus. Using the relation, we know that G is equal to E upon 2 into 1 plus mu. So the distortion energy I can write in terms of a second invariant of our deviatoric stress tensor and a shear modulus as UD is equal to 1 upon 2G into J2. And this is an important relation between us J2, that is second invariant of our deviatoric stress tensor, with a distortion energy. Now let's move on. So what von Mises yielding criteria says now is that yielding will happen when J2 reaches a critical value, and it says that the value is k square. So when J2 becomes equal to k square, we will have yielding, or material will start to yield. So from a tensile test, we get the yield stress, say sigma y. Let's consider that a tensile test over here, and I have a stress which uniaxial tension which I am applying as sigma 1, and here sigma 2 equal to sigma 3 equal to 0. So this is what a stress state we have, and we can find out J2 for this given stress state, that is a uniaxial tension. So I write J2 as 1 upon 6 sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. So we have found out this J2, and now we will replace that sigma 1 to be sigma y, that is at yielding I consider sigma 1 equal to sigma y. So when the value of sigma 1 reaches sigma y, the material will start yielding. So I put these values in this relation, and what I get is that J2 is equal to 1 upon 3 sigma y square, and I can find it out sigma y, that is yield stress in terms of a J2, that is second invariant of deviatoric stress tensor, and I can find it out when the yielding will start. So when yielding will start, when the sigma y, that is an yield stress value, reaches root 3 times under root of J2, or sigma y square is equal to 3J2. So for a general case, I can say that I can replace this J2 with principal stresses and these values. So I can say that when the yield stress reaches 1 upon root 2 times square root of sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. So when the yield stress reaches this value, the material will start yielding. So we have figured it out when the material will start yielding. From a given stress state, we convert it into a principal stresses, and from that we found out what is a J2, which is nothing but a second invariant of our deviatoric stress tensor, and we found out what is when our material will start yielding. Now let's apply and check three consistencies. So three rules which we have seen. The first rule was the hydrostatic stress state will not cause any yielding. So you apply here in hydrostatic stress state, you will have sigma 1 equal to sigma 2 equal to sigma 3. So that means if I put sigma 1 equal to sigma 2 equal to sigma 3, so this whole term will turn out to be 0. So the first condition is satisfied. The second was your deviatoric stress state only will cause yielding. So this we have found it out, this relation we have found it out using second invariant of deviatoric stress tensor. So thus the second consistency is also met. And the third consistency is, or third rule is, this relation should be independent of your coordinate transform. This J2 is itself is an invariant term. So the third rule or the third consistency is also met here. So this is our von Mises criteria. Now let's look at this von Mises criteria based on strain energy, that is a distortion strain energy. So von Mises criteria says that when a strain energy reaches a maximum value or the maximum distortion value, then the yielding will start. So this von Mises criteria is also referred as maximum distortion strain energy criteria. So we have seen that the distortion strain energy, that is elastic strain energy taken into account of a deviatoric stress tensor. We have found it out, and So we got this relation as UD is equal to 1 upon 2G into J2. Now let's consider a uniaxial tensile test again. So we have sigma 1 which is acting along a tensile axis, and you have sigma 2 equal to sigma 3 equal to 0. So at yielding, this sigma 1 we can consider it equal to yield stress of a material, and thus I can write J2 as 1 upon 3 sigma y square. This we have seen in our previous slide. So at this condition, that UD, that is nothing but a distortion energy, becomes a critical or a maximum distortion strain energy, and I call it as UD star. So this UD star, I can write it as 1 upon 2G. I use this relation and I put this value which is at an yielding. So it comes out to be 1 upon 3 sigma y square, and so UD star is equal to 1 upon 6G sigma y square. So we get this relation. And now for a general case, what I do is that I compare this UD star with this value. So 1 upon 6G sigma y square is equal to 1 upon 2G J2. And what I get, the relation which we got in our earlier slide also, that sigma y is equal to under root of 3J2. So this is a relation by which we can find out when the material will start yielding. So when the sigma y reaches or becomes equal to root of 3J2, where J2 is nothing but the second invariant of your Deviatoric stress tensor. When this criteria is met, the material will start yielding. Now let's see another criteria, that is a Tresca criteria. So we have seen a von Mises criteria. Now we will see a Tresca criteria. So the Tresca criteria says that the plastic deformation occurs because of shearing. Shear stresses are important to find out when material will start deforming plastically. So we'll revisit this when we will be discussing the slip deformation, why shear stresses are important and why shearing causes a plastic deformation. So this is a maximum shear stress criteria. Von Mises criteria was a maximum distortion energy criteria, and Tresca criteria is maximum shear stress criteria. So when we say that tau max, that is a shear stress, maximum shear stress reaches yielding value, that is tau y, then the material will start plastically deform. So where tau y is a critical shear stress or a yield stress. Now let's consider stress state where you have principal stresses as sigma 1, sigma 2 and sigma 3, and where sigma 1 is greater than sigma 2 is greater than sigma 3. So we have seen this 3D stress state, or when we discussed about Mohs circle, and we figured it out what is the maximum shear stress experienced at what planes. We have seen this earlier when we spoke or when we discussed about 3D stress state using Mohs circle. So here in this case, where sigma 1 is greater than sigma 3, we have seen that we get a maximum shear stress at this xz plane, where tau max, you can write it as sigma 1 minus sigma 3 upon 2. So we have this tau max to be coming at xz plane, to be sigma 1 minus sigma 3 upon 2. And when we consider a uniaxial tensile test again here, I have sigma 1 and I consider sigma 2 equal to sigma 3 equal to 0. So I just have only sigma 1. At yielding, we can consider this sigma 1 to be equal to sigma y. And thus, according to Tresca criteria, we say that tau max equal to tau y. So I can compare this tau max equal to tau y, which is nothing but sigma y by 2. So I see here that when I plug in these values, sigma 1 equal to sigma 1 and sigma 3 equal to 0. So I get sigma y by 2. And that's what I can find it out, that tau max equal to sigma 1 minus sigma 3 upon 2 equal to sigma y by 2. So I can write that sigma 1 minus sigma 3 equal to sigma y, and this is our Tresca criteria. So yielding starts when this condition is met. So when I have sigma 1 minus sigma 3 equal to sigma y, which is nothing but yield stress of a material, when this condition is met, the material will start yielding. So let's now see what are yield surfaces. So let's consider a cube and it is subjected, and let me mark my coordinate axis, and lets the principal stresses acting on these three surfaces to be sigma 1, sigma 2 and sigma 3. So when you consider 2D stress state, sigma 3 equal to 0, and let me plot sigma 1 and sigma 2 origin over here. And according to Tresca criteria, what you can see that when sigma 1 minus sigma 2 is less than equal to sigma y, the material will start yielding. We have seen this in our previous slide. So based on the values of sigma 1 and sigma 2 and sigma 3 and yield stress, you can find out what can be the criteria for yielding. So here in this case, you have sigma 3 equal to 0. Let's say I have a sigma 1 which I am applying and sigma 3 is 0, so you can get a maximum value. Let's say sigma 1 is greater than sigma 2, so you will get maximum value satisfied by this relation where sigma 3 is 0 and sigma 2 is positive. Let's say I am in this quadrant. So material will start yielding when sigma 1 reaches sigma y at this point when sigma 1 is positive or a tensile in nature. Similarly, it will happen when sigma 1 will be in a compression. What I can say, sigma 1 reaches sigma y. This is another point where material will start yielding, where sigma 2 and sigma 3 are 0. Now similarly, when you apply sigma 2 and sigma 1 and sigma 3 are 0, what we get is that when sigma 2 reaches sigma y, material will start yielding. Similarly, in compression, when I apply compressive stress along x2 direction, so you will have yielding when sigma 2 reaches to minus sigma y value here. So at this point, material will start yielding. Now you have sigma 1 and you have some positive values of sigma 2. So basically, if we are in this quadrant and sigma 3 equal to 0, what you can say that the maximum value or the maximum value reached will be by this relation only, sigma 1 minus sigma 3. So here it is 0, so you will get sigma 1 which is less than equal to sigma y. So you can basically see that material will start yielding above this point of sigma 1 because sigma 2 is positive. When sigma 2 is positive and sigma 1 also is positive and sigma 2 is greater than sigma 1, then this relation will be valid over here, that is sigma 2 minus sigma 3 is less than equal to sigma y. So basically this is the line which will be represented by this relation. So let me write it down. So here you consider sigma 3 minus y less than equal to sigma y, whereas this will be sigma 2 minus sigma 3 less than equal to sigma y. So these are the two conditions which we can see that if the stresses are above than this, you will have yielding of a material. Similarly, you can see the same behavior in this quadrant, that is a third quadrant, where both sigma 1 and sigma 2 are negative. Basically, you will get the same relation over here. Now, so when I consider this region where sigma 1 is negative and sigma 2 is positive, what you can get here is that you will get a maximum shear. Let me write it down. So we will get it maximum shear here to be sigma 1 minus sigma 2 to be less than equal to sigma y. So basically sigma 1 is negative and it adds up with sigma 2 and the total value will be more than any of these two equations. So you get this relation which is nothing but a straight line which is joining these 2 points. Similarly, you get the same relation of between sigma 1 and sigma 2, the straight line over here. So this is an yield surface which is defined by using Tresca criteria. According to Tresca criteria, if the stress state is between these regions or inside these boundaries, let me write it down. So when the stress state is inside these boundaries, this hexagon, then the material will not cause any yielding. So here you don't have any yielding, will not be any yielding. And as soon as the stress state is crosses these boundaries, the material will yield. Now let's consider von Mises criteria. So according to von Mises criteria, we have figured it out that sigma y is to be 1 upon root 2 into sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 whole square under root of this whole term. So we have seen this relation. Now let's consider this a 2D stress state and put sigma 3 equal to 0. So I can find that sigma y square is equal to sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square. This is the relation which you get. So if you see this relation carefully, what you find is that this is an equation of an ellipse. So if I find out, or if I put the values of sigma 1 and sigma 2 and try to find out the loci, I get this as ellipse. So this ellipse is representing an yield surface. So what I can say that if the stress state is confined by this ellipse, you will not have any yielding. If the stress state is falling outside of this surface, or there will be an yielding of material, or the material will deform plastically. So these are two yield surfaces defined by Tresca criteria and von Mises criteria. So this we have seen it for 2D stress state. Now if you look at this von Mises criteria carefully, you can see that sigma 1 minus sigma 2 is nothing but a diameter of Morse circle, and sigma 2 minus sigma 3 is the diameter of Morse circle between sigma 2 and sigma 3, and sigma 3 minus sigma 1 is nothing but a diameter of Morse circle between sigma 1 and sigma 3. So this, if you see this relation, this is a square root and these are the diameters and their squares. So this von Mises criteria are nothing but a root means square diameter of 3 Morse circle. So this is another way of looking at von Mises criteria in terms of diameter of Morse circles. Also, what I want you to find it out, the ratio of the length of major axis and minor axis of this ellipse, and see that whether it comes as root 3:1. What you have to do is that find out this length and this length. Here you can say that this length sigma 1 is equal to sigma 2 and can find it out what is this length. Similarly here you can say that sigma 1 equal to minus sigma 2 and find out this length. So whether you get the ratio of the length to be as root 3:1. Just check it out yourself. Now we have seen this in 2D stress state. Now let's look at 3D stress state. So what will be the 3D stress state? It will be the loci of all Tresca criteria and von Mises criteria, or all these yield surfaces. So when I see a loci of all these yield surfaces, how will it look like in 3D? It will look like as a cylinder or like distorted cylinder for your von Mises yield surface, and for a Tresca pyramid shape. So you can see that you have yield surfaces in 3D where the axis of will be represented by an hydrostatic stress state where you have sigma 1 equal to sigma 2 and sigma 3, and this loci or this plane is contained by a deviatoric plane where you have, or which is called as pi plane also, where sigma 1 plus sigma 2 plus sigma 3 equal to 0. So you can figure it out what is a pi plane over here, and you can figure it out if this axis really represents a hydrostatic stress state. And the surfaces for von Mises yield surface and Tresca yield surface, which we have shown over here. which are nothing but the loci of such surfaces. So with this, you can understand now for a given stress state why we are finding out principal stresses or principal planes, because the ultimate goal was to find out when the material will start plastically deform. So whatever the exercises we did to find out principal stresses using eigenvalues or eigenvectors, their locations, is to figure it out when the material will start yielding. So you can appreciate now why a given stress state we have to find out principal stresses. With this, I will stop here.